Physical changes normally can be reversed. We might have a new shape or a size. We might have a new state of matter. Maybe we melt that ice cube. Maybe we boil that pot of water. Those are signs of physical changes. So we could take the steam from the water and condense it and get it liquid water again. So we didn't change what the substance was. It's still H2O. It's still water. Signs of a chemical change, the substance will change. The atoms rearrange. There's bonds that are breaking and reforming. Generally, it is not reversible through just physical means. Perhaps that you could do another chemical change to get it back, but sometimes it's too hard to go backwards. So an unexpected change in color, maybe you take two clear solutions and you put them together and you get a purple solution. That would be unexpected. There might be an odor that is released or a gas that's released. You might see a solid form, which is called a precipitate, and your test tube or your reaction container might heat up a little bit. So that is a sign of a chemical change. We're going to learn three new types of reactions, and the first one is called a precipitation reaction. This is a double replacement reaction, but specifically the product formed is a solid. So anytime you have a solid form on the product side, that's a precipitation reaction. And if they do include the species, you're going to see that we have some compounds that are dissolved in water. And then when you pour them together and they react, we get a precipitate or a solid. And then this is just the leftover. So what's happening here is the attractive forces between the lead and the sulfate are stronger than that of the water that's surrounding each of the ions. And so a precipitate is formed. These are all the solubility rules. However, the AP board has simplified the process. If you know the ones in blue, you're going to be okay. Through deductive reasoning, you can figure out what the answer would be on a multiple choice question, and you can also figure it out on a written exam. So first of all, you need to know that alkali ions, so that's the first family of the periodic table. So that would be lithium, sodium, potassium. They are always soluble. So when you put a compound that has an alkali ion in solution, it will always dissolve. Also, ammonium, NH4 plus, a compound containing that will always dissolve. And nitrate, NO3 minus. If you put a compound with a nitrate in the formula into water, it will always dissolve. If you have anything else that's not an alkali ion or an ammonium or a nitrate, then assume that it's going to make a precipitate. So if you just memorize these three, you are going to be okay. Which one of the following will be a precipitate if formed in a precipitation reaction? So let's look at this first one. So on this first one, I see that there's a nitrate. See that NO3? So I know that this won't make a solid because this one's always soluble. Let's look at the next one. Oh, there's another nitrate. Again, it's always soluble. And let's look at the third one. I see an alkali metal, that Na plus would be the ion. That is always soluble. And that comes to our last one, the only one left. Which of the following will precipitate? It's this one. So silver chloride, that is a solid. So if I take silver nitrate in one test tube and I take potassium chloride in another one, they will dissolve. But when I pour them together, I am going to get a precipitate that forms on the bottom. And then my leftovers will be the nitrate and the potassium because they always dissolve. The ones that will form the compound will be silver chloride. So in a problem like this, you can see how you can eliminate some of the possible answers just knowing alkali metals, nitrates, and this one didn't have ammonium, but if ammonium was there, eliminating those, and then your answer will be the one that's left. A second type of reaction is an acid-base reaction. It's also known as a neutralization reaction. It's where you take an acid and a base and you put it together and you get a salt and you get water. So notice that water is formed, it's a liquid, and then you have your leftover, which is your salt. You also can remember neutralization reactions as AABC. An acid donates the ion, the base donates the cation, and so that might be something that you can use to watch out for. Here are some neutralization reactions with gas formations. The equation part of the AP exam was taken out, but sometimes you'll have to analyze an equation. And so you want to look out for these carbonate compounds. So carbonate is found in things like baking soda. And anytime you see these carbonates, these CO3s, know that generally you will make carbon dioxide. So this will be carbon dioxide gas. In this second equation, we see that we form some intermediates, and then we see that this goes on and forms our bubbles, our gas. So again, watch out for those carbonate compounds and just know that if bubbles are forming, it's probably going to be carbon dioxide gas. Okay, the third type of reaction that we're talking about today are oxidation and reduction reactions. They're also known as redox reaction. The re from the reduction and the ox from the oxidation we put together and have redox. These are single replacement reactions where you have an element come and kick out the cation and it becomes the new element, and that's called single replacement. Single replacement reactions are always redox reactions. In a redox reaction, we have something that is oxidized and something is reduced, and what that means is that the oxidation numbers change. Or you can just memorize if it's a single replacement reaction, it's going to be a redox reaction. Let me show you what I mean by the oxidation numbers changing. So zinc is neutral, so it doesn't have a charge. But in this next compound, the copper 2 nitrate, I have that the copper is a +2 charge. I know that because NO3 is a minus charge and I have two of them. So all of that is a -2. Now look on the other side. Now copper is all by itself, and when I just have a metal atom, it's a neutral charge. And let's look at the zinc nitrate. My zinc is a +2. So we see what has happened here. My zinc has lost electrons. Remember, electrons are negative. And my copper goes from a +2 to a 0. It has gained electrons. So this is a redox reaction when electrons are gained and lost, or they are exchanged in the reaction. And you can remember the little saying, oil rig, oxidation is losing, reduction is gaining, so that I know that my zinc is being oxidized and my copper is being reduced. I just want you to be able to recognize the types of reactions. So I've combined these three reactions with the three that we learned earlier. Stop the video and go ahead and classify each of these 6 reactions. Okay, let's go over the answers. So on this first one, I see that I have an acid plus a base. So this is a neutralization reaction. On this next one, I see that I have an element and a compound, and I get a new element. This is a single replacement reaction or a redox reaction. This next one, I have one thing going to two things. So this is a decomposition. Number 4, I see an acid and I see a base. So this is also a neutralization reaction. You can see that water's formed. That is another sign of a neutralization reaction. On this next one, I see that there's a solid that's formed right there. And so this is a double replacement. It is also a precipitation reaction. And number 6, I have two things that are going into one thing. So this is a synthesis. And which type of reaction is missing? It would be combustion. Remember, in combustion, you have a hydrocarbon plus oxygen, and you get CO2 and water, always. So you should always have oxygen, CO2, and water. If one of those is missing, it's not combustion. If one of those is missing, it is not combustion. And you can also have oxygen here with your hydrocarbon. I just want to mention electrolytes here. Electrolytes are ions that conduct a current. A strong electrolyte is one that dissociates completely when it's dissolved in water. So this would be all salts, strong acids, and this should read strong bases. A weak electrolyte only dissociates partially when dissolved in water. So this will be your weak acids and weak bases. And a non-electrolyte does not dissociate in water. So anytime you have something that still dissolves, but it stays together in the water, this would be something like sugar or alcohol. So on your homework and on the test, I will help you with knowing if it's strong or weak. As I said before, non-electrolytes are molecules that dissolve, but they don't carry a current. An example of this is sugar. So sugar has these little OH groups on the end, and because of that, they are attracted to the water, and that enables them to dissolve, but the sugar molecule doesn't split up. As a result, it does not carry a current. The AP board likes all precipitation reactions to be written as what's called a net ionic equation. So when you have an ionic compound put into water, so this is when you have a metal cation and a nonmetal anion, and those are put into solution, they will split up into solution. They'll just be floating around, the water will be surrounding it. And when you put them together, here I have my lead ion and my sulfate ion. They are more attracted to each other than they're attracted to the water, and so they will form this solid. Well, I have some leftovers over here, and these are called spectator ions. So these spectator ions, they're just like a spectator in a sporting event. Like when you watch tennis, the spectators just move their heads back and forth watching the tennis match. And it's the same thing in chemistry. I have these anions and cations that are leftovers that don't participate, but they're just hanging out there in solution. So what a net ionic equation does is get rid of those. So the in real life, that reaction has to have those spectator ions. But when we're just trying to distill and write just what is happening, that is when we write a net ionic equation, and we're only going to include the things that make the solid. So we're only going to include the lead and the sulfate. So when you're writing net ionic equations, you always want to include solids, liquids, and gases on the product side, and let them be your guide. So if there's a solid, a liquid, or a gas that is formed, it for sure is going to go on the product side, and then you can work backwards. You can write down that product that's a solid, liquid, or gas, and then you can, on the left-hand side, put the reactants together that will make that solid, liquid, and gas. So watch out for anything that's aqueous because it possibly could be a spectator ion. And remember, in these problems, we want to omit the spectator ions. So this is that last problem with the lead 2 sulfate. And I'm just going to teach you how to write just the net ionic equation, and then I'll do the complete ionic, kind of working backwards. So on this problem, to write the net ionic, I'm going to find the solid, liquid, or gas. In this case, it's the solid. And then I'm going to figure out, well, what went into that solid? Well, I know the lead went into the solid, and I need to figure out what the charge of that is. And I can come over here and I can say, okay, each of these nitrates is a -1, so that gives me a total of -2. So that means that this lead must be a +2. And so I want to include that charge there. And then the next one, so I know that the potassium will always dissolve, so that's not going to make my solid. And plus I know my solid is already lead sulfate. So this is a polyatomic ion. If you don't know the charge, you can look it up. You can also figure it out from up here, because I know that the potassium's a +1 and there's 2 of them for a total of +2. So that means that the sulfate must be a -2. So there is my net ionic. You could put the aqueous in, but if you forget it, I'm not going to mark you wrong. Okay. So what's really happening here is when I put the lead nitrate into solution, it splits up into its ions. So there's that first one. And then the second compound will split up into its ions. And then your solid, liquid, or gas that's formed on this side, always keep it together. All right, so I write that complete ionic equation, and then you can look for duplicates. So these are your spectators. Your spectators are going to find on both sides. So I have 2 NO3 and 2 NO3. I have my 2Ks and my 2Ks. And so then what is left, that is your net ionic equation after you get rid of those spectators. So this is just another way to do it. So again, you can either start from the solid or liquid or gas and then work backwards, Or you can write out the complete ionic where you separate it into its ions with the correct charges and everything's balanced. And then you can eliminate the excess, which are the spectator ions. So let's look at this reaction. First of all, what type of reaction is this? Well, it starts with an H and this has an OH. So this is a neutralization reaction, or it's an acid-base reaction. The complete ionic, OH minus, is a polyatomic ion. Notice that I keep the liquid together, so don't split up your solids, liquids, and gases. So I can eliminate the spectators. So I have K on each side, I can get rid of that. I have NO3 on each side, I can get rid of that. And so I will have H plus OH minus, and I'll get liquid water. You could also start from the liquid water and then work backwards trying to figure out what ions would make up the liquid water, but you would end up with the same thing. You can put the little aqueous species there. Okay, let's do a problem where we write the reaction from just a word problem. So we have potassium hydroxide reacting with zinc sulfate, and this one is going to be a double replacement. So I'm going to get potassium sulfate, and I'm going to get zinc hydroxide. So let's write out the formulas. So potassium is a +1, looking on the periodic table. Hydroxide is a -1. Zinc is a +2. And sulfate is a SO4 2-. So let's go ahead and put these together. So I have KOH, those just get put together. I have zinc sulfate and potassium sulfate. I'm going to need 2 of these to cancel out the sulfate, and zinc, I'm going to need 2 of the hydroxide. This is not balanced. I would have to balance it, and I already did the balanced molecular reaction right here. The complete ionic, I'm going to separate out in just a minute. But looking at this, where's my solid? Where's my precipitation reaction, this double replacement? It's going to be the zinc. And I know that because the potassium always dissolves. So working backwards, I'm going to take my zinc, which is a +2, and my hydroxide, which is a -1. And then to balance it, I do need a 2 in front. So there's my net ionic. That is a reaction that occurs. We could go and split this whole thing in the complete ionic. So first everything's split up into its ions. And then on this side, I know that the potassium splits up because it always dissolves. But this zinc hydroxide is going to stay together because that's the point of the reaction, is I made a solid. So we can eliminate the spectators. So I have potassium on each side and sulfate on each side. And then I get basically the same thing. It's okay if it's in a different order. Okay, so those two come together and make my solid. So this is predicting the products and writing the net ionic equations. So you're going to be making a solid, liquid, or gas on these. This first one is a precipitation reaction. And the precipitate that I'm going to be making, where nitrate and sodium are not going to make a precipitate, the leftover is going to be the silver phosphate. And so that's going to be my solid. And then I do have my spectators. That is going to be the sodium nitrate. So writing out the solid and working backwards, I'm going to have silver, which is always a +1, and the phosphate, which is a -3. And just making sure it's balanced, put a 3 in front. Looking at this next one, I have an acid base. And so I'm going to make salt water, and water that's the liquid. And so then I just put what's with it, the acid part and the base part, and I get liquid water. This next one looks like it's going to be a synthesis. And sulfur has a -2 and sodium has a +1. So it's going to look like that. and I'm done. Okay, that's the net ionic. There's nothing else left. And it is balanced. Let's do this next one. So this must be a combustion because I have my hydrocarbon and my oxygen. So CO2 plus water, and we can balance it. 4 and 6. 5 looks like a precipitation reaction. And if I had to guess, well, I know that this won't precipitate. So that means my sulfate is going to be in a solid, and the only other cation there is barium. So I'm going to do barium sulfate, and then my leftover. The net ionic, therefore, would be barium sulfate is my solid, and barium has a +2 charge, and sulfate has a -2 charge. So that's a precipitation or a double replacement reaction. And let's look at this next one. This next one looks like it's a single replacement or a redox reaction. And so these two are going to switch places. So I'm going to have magnesium chloride plus my copper and balance it. And so those are the products, and that is net ionic because it's redox, so you just include everything. So this is more of an advanced topic. I would be happy if you could classify these and then maybe take a guess on the products. But this is more advanced. I would think that the AP board would shy away from this a little bit, but this might help you with a multiple choice question.